Welcome back. So, before the break, I discussed the path integral solution for a path independent option, a Black-Scholes option, an option which is whose payoff is independent of the path followed by the price of the underlying asset, and also the option is exercisable only on maturity. We now relax this assumption and we say that we want to evaluate an option which is path dependent. In other words, the payoff on the option depends on the path followed by the price of the underlying asset. So, now let us look at this problem. So, in this case the payoff at expiration of the option, payoff at maturity of the option will be written in the form of the expression given in the red box here. Please note the difference compared to what we had in the earlier case. In the earlier case, we had the payoff written as f as a function of s of t, where t is the maturity date. Here we are having f as a function of s of t dash, where t dash is any point between the up to the maturity of the option. So, f s t dash is now a functional on the price paths given by these expressions, that is the price that is the value of the stock or the price of the stock from today onwards up to the date of maturity of the option. We assume that the stock price follows the risk neutral price process that is given by this expression. Just to recall, dz is the infinitesimal Brownian motion increment, standard Brownian motion increment, and same as dw, and we have mu is equal to r minus sigma square upon 2, that is the drift term, and the diffusion term is given by the component or by the term sigma. The present value of the path dependent option at the inception of the contract T, that is as of today, is given by the Feynman-Cach formula. We have seen this earlier. The only difference is that in the payoff in the earlier case is substituted by the payoff now, which is path dependent, and the path integral is also changed. Path integral is again the expression within the round bracket, brackets here. The change is essentially, if you look at it carefully, it is essentially in the payoff term f e to the power x t dash. Now, it is a function not of x capital T, but of x t dash. Now, because f e to the power x t dash, remember x are logarithms of prices. So, please take note of that. F e to the power x t dash depends on the entire path. You cannot simply move it outside the path integral as you did in the Black-Scholes case, as you did in the path independent case. So, now we consider a simplifying case to illustrate the methodology in the sequel. We take a simplification, we take a special case. We assume that the payoff functional f can be represented as a combination of two terms. We write f as small f s of t, where small f is the payoff that relates to the stock price at maturity, that is dependent on the stock price at maturity, and another component which relates to the path followed by the stock price. So, f s capital T depends only on the terminal asset price, and I s t dash is a functional on price paths from t comma s, that is today, to capital T to s capital T. Remember, this particular term, the second term captures the path dependence, and the first term is a scaling term that relates it to the, or that is dependent only on the terminal price of the underlying asset. And we can write this I s t, or we assume that I s t can be written as a time integral of a potential. We assume that I s t can be written in terms of a time integral of a potential given by the expression in the red box here. We introduce a potential term such that IST becomes the gradient of that potential with respect to time, or putting it the other way around, IST is the time integral of the potential with respect to is the time integral of the potential. Is there, or you can say that we introduce a term potential such that this equation is met. Then the Feynman-Cag formula or the path integral formula can be written in the form which is given here. Please note the difference compared to the earlier case. We because small f e x t depends only on the terminal price or the terminal logarithmic price or logarithmic prices mean the same thing. Therefore, it can be taken outside the path integral. This component of the price can be taken outside the path integral, and the second part, that is IST, that is the path dependent component, is captured or it is retained in the path integral, and that is incorporated therein by this factor of the potential, as you shall see just now. And we have this transition green function or transition amplitude k v x t t x t. This is the path integral component. K v x t t x t comma t is the path component, path integral component. So, k v is the green function that relates to the zero drift Brownian motion, but in the presence of a potential term v x t, where the potential term is itself related to the payoff of the underlying asset, payoff of this derivative, I am sorry, payoff of the option by this particular expression in the red box. So, k v is given by this expression, this path integral, which is here in the red box here, right at the bottom of your slide. And so, this is the Feynman-Cag path representation, and it is the fundamental solution, path integral representation of the fundamental solution of the zero drift diffusion equation with potential, zero drift diffusion equation with potential V x comma t, and the diffusion equation is shown in the red box here. The initial condition, as was the case earlier, is shown in the green box here. The option price which we will obtain on solving this particular set of equations will satisfy the Black-Scholes equation, but with an additional potential term which is shown in the green box here. So, this is the way we can this is the skeleton of the way in which we can obtain solutions to the path dependent option problem. You see, the problem is that in such situations, in such cases, it is more often than not the case that closed form solutions are not possible or not obtainable, and therefore, the only way out is to obtain numerical solutions through numerical integration or numerical solution of the differential equations or numerical estimation of the path integrals. But nevertheless, the message that is conveyed here is that by using the concept of path integrals, we are able to have a versatile tool by which we can attack such problems and resolve such problems in cases where the payoffs are highly complex, highly intricate. Now, what I propose to do is, I propose to highlight some more applications of the path integral formalism in the context of finance and related areas. Now, let us talk about the zero coupon bond. A zero coupon bond is a bond that is usually sold at a discount, and it is redeemed at par, and it does not pay any coupons, it does not pay any interest during its life. In other words, it is sold at a price below its par value, and on the redemption date it is redeemed at its par value, and the difference between the two constitutes the yield, constitutes the return for the investor. The zero coupon bond, as its name implies, does not pay any interest coupons during its life. So, suppose we are to evaluate a zero coupon bond, we have to work out the current price of a zero coupon bond. Let RT be the instantaneous interest rate, T is at time t, RT is the instantaneous interest rate at time t, and capital T is the maturity of the bond at which it will pay 1 unit of money, which is its face value, which is its redemption value, and capital T is its maturity, as we have been denoting earlier. Then the current price of the bond is the present value of the future cash flow, that is the redemption value, because there are not going to be any coupons. So, it is going to pay only the redemption value. So, the current price will be the present value of its redemption or face value or redemption value, as the case may be. If in case they are not identical, then of course, it will be the redemption value. But the important thing is, when we work out the present value, the interest should be the relevant interest rates prevailing during each instant of the period of time between today and the maturity of the bond. That is what is captured by RT, and therefore, putting it into the form of an equation, what I have just stated is that the current price of the bond is the expected present value, and this is what is present value of the, because the principal value is 1 or the redemption value, principal value, face value is 1. So, we in that factor goes, and this is the expectation of the interest rates prevailing over the life of the bond. Now, here the variable r tau is the instantaneous interest rate prevailing at time t equal to tau. Today is small t and maturity is capital T. Keep that at the back of your mind. And the stochastic differential equation can be obtained from corresponding to the Lagrangian, which is given in the green box here. And we define the expression the matrix elements, in fact, as we have done in the case of quantum mechanics, as the expression that is there in the red box, and in terms of the path integral, this matrix terms or the matrix elements take the form which is given in the green box here, where L tilde is the Lagrangian, modified Lagrangian, which is given by the expression right at the bottom of your slide. And using this expression for G, we can obtain the value of the price by integrating this expression between minus infinity and plus infinity with respect to the interest rates. At maturity. Now, we talk about the harmonic Lagrangian, because it has an application to a very important interest rate model. The harmonic Lagrangian is given by this expression here. Just recall that this Lagrangian is very similar to the Lagrangian that we worked out for the harmonic oscillator, which we solved for in the context of the quantum mechanics. It is absolutely similar. The Lagrangian is absolutely similar, except for a sign difference here. There we had a minus sign, here we have a plus sign here, and the Lagrangian does not contain any cross terms here. The solution to the path integral can be obtained in absolutely the same way as we have obtained the solution using Fourier transforms in the case of the quantum mechanical problem of the harmonic oscillator, and the solution that we obtain is given in the red box here, where sigma bar is taking the expression given in the green box here. Then Now the harmonic Langevin equation. This is the equation that is given in the red box here is the harmonic Langevin equation, and the corresponding Lagrangian is given by the expression here in the green box. And now this expression, if you look at the Lagrangian here carefully, this Lagrangian is very similar to the Lagrangian in the earlier case, immediately preceding case, the harmonic Lagrangian, except that there is a coupling term between x and x dot, and there is a constant factor as well. The finite time transition probability we can obtain again in the same way, and it is given by the expression that is here in the red box. And the path integral in this case, path integral that we have here in this finite time transition probability, rho x capital T y t, this particular part, the second part, that is the path integral part, is the same as we have for the harmonic case, for the harmonic oscillator, or the harmonic case that we discussed just a few minutes back, just before the Langevin equation one. And putting that value here, we get the expression for the transition probability as the expression that is here in the red box, where sigma bar is given by this expression right at the bottom of the slide. Now, Wassesek model is a very important model for short term interest rates, and the model is described by the equation that is given here in the red box, where the randomness is captured by the second term, and the first term is giving the drift. The second term gives the randomness as delta W is again the infinitesimal Brownian motion increment, delta R is the change in interest rates, and we obtain the finite transition probabilities in this model, the Wassesek model, by the path integral, which is given here in the expression in the red box, where the Lagrangian takes the form which is given here in the green box. Now, as you can see, if you simplify this case is similar to the harmonic Langevin equation with the substitutions omega is equal to a and x is equal to r minus b. The path integral can be worked out simply by using the results of the harmonic Langevin equation, and we get the expression which is here in the red box, where L tilde is the modified Lagrangian, which is given by the expression in the green box here. By making this linear change in variables that is given in the red box here, we are able to do some simplification. We can write the modified Lagrangian L tilde in the form which is given in the expression that is in the red box here. Now, if you look at it, the last three expressions can be integrated straight away, and they give rise to a phase factor, and the phase factor is captured in the prefactor, that is e to the power minus delta theta, and the rest of the terms are retained in the path integral. Delta theta is given by this expression, which when simplified can be written in the form of this expression. And as far as the remaining path integral is concerned, we can use the results of the harmonic Langevin equations, and we can arrive at the result which is here in the red box, with sigma bar given here in the red box as the modified standard deviation of volatility. Now, some important properties of Black-Scholes equations, quickly let us run through them. Now, the conditional expectation of stock price, if you look at this, the conditional expectation of stock price E of ST, remember we are talking about as on maturity. So, E of ST subject to ST is greater than or equal to k, log of x is a monotonic function of x, we can write it in the form expectation of E log of st, E st is greater than equal to E log of k. The same thing, they mean the same thing, because a log of a variable is a monotonic function of the variable, and therefore that being the case, we can now substitute log st as xi, and we get the expression that is given in the second line of the red box, which we write as a, where xi is equal to log of st, and remember log of st is normally distributed with a mean of log s naught plus r minus 1 by 2 sigma square t comma sigma square t, mean of this and a variance of this. Remember, we are working in a risk neutral world. We substitute this log s0 plus r minus 1 by 2 sigma square t as lambda, and sigma square t as we retain as it is. So a is equal to this expression. Now the integration variables y log k to infinity, because we want to find out the value of st subject to st is greater than k, which in terms of the new variable means that we want to find out the expectation of e to the power xi subject to xi greater than log k, e to the power xi subject to xi greater than log k. That is precisely what is there. And when we do the simplifications, when we do this lot of simplification, lot of algebra here, and after doing all this algebra, what we end up with is s0 e to the power rt phi d1. So this is what this is the conditional expectation of the stock price finishing in greater than the exercise price of the option, s0 e to the power rt phi d1. Now what is the need for this? Let us see. Interpretation of phi d1 and phi d2 and the Black-Scholes solution. That this is an important point. So let's quickly do it. C is equal to, this is the formula that we have standard, used it again and again. So we can, for the Black-Scholes call, the payoff is maximum st minus k comma 0. So we write it as it is. So C can be written as e to the power minus rt e to the, and in the Black-Scholes model, C is equal to s naught phi d1 minus k e to the power minus rt phi d2. You take e to the power minus rt common, you get this expression inside the square bracket. The first component of payoff is, let us analyze. First component of payoff is minus k. Minus k is what? The payment of the exercise price by the holder of the call option. That will be payable if the option is exercised, and if the option is not exercised, it will not be paid. So this component of the payment, let's call it C1. C1 will be minus k if st is greater than k. If the option is exercised, then I will pay this particular exercise price and 0 otherwise. Now if the probability of st greater than k is given by phi of d2, so E expected value of this is equal to minus k p st greater than k into 0 into this is simple. So minus k into this is minus k phi d2, because probability st is greater than k is nothing but phi of d2, and therefore this is as far as the first component, but because this is going to happen at maturity, its present value is e to the power minus rt k phi of d2. This is as far as the exercise price is concerned. Second component of payoff is what I am going to receive. I am going to receive the stock which I can sell in the market at st, but therefore the second component is st if st is greater than k and 0 otherwise. Therefore the expected value of the second component is E st greater than equal to k plus 0 this thing, and this is equal to E st subject to st is greater than k, which we have just now evaluated, which is E rt s0 phi d1. So s0 phi d1 is equal to present value of this second component, and therefore when we substitute these values, what we find is that the Black-Scholes formula is also based on the premise that the value of the option is the present value of the expected payoff from the option at maturity. Risk neutral valuation of Black-Scholes. This is we start with this formula, we simplify this, start with this formula which we have been using, e to the minus RT, risk neutral probabilities. We substitute the payoff for the call option maximum ST minus K comma 0, that gives us e to the power minus EQ ST minus K subject to ST greater than K, because the option will be exercised only if ST is greater than K, otherwise the payoff will be 0. So, and because the payoff will be 0, it will not contribute to the expectation, and therefore if ST is less than K, there will be no contribution to the expectation value. This can be written as EQ ST subject to ST greater than K minus EQ K subject to ST is greater than K, that is EQ. This we have already obtained in previously as this expression, and this is EQ, that is K into ST greater than K, and that is nothing but N phi d2 or N d2, and again we arrive at the same formula using the risk neutral derivation. Then we have got some problems here, some examples. If a stock price if a stock follows geometric Brownian motion with an expected return of 16%, mu is 16%, volatility is 35%, the current price is 38. What is the probability that a European call option on the stock with an exercise price of 40 and a maturity date of 6 months will be exercised? So, that is a question. We see, remember the possibility of exercise, or the probability of exercise is equal to the probability that the stock price exceeds the exercise price. Stock price exceeds the exercise price, the probability of that is phi d2. So, we simply have to work out phi d2. So, we can work out on d2, work out phi d2, and that will the solution. The alternative problem is to start from first principles. We want the probability of the stock price being more than 40 in 6 months time. Suppose the stock price on maturity or at the end of 6 months is ST, then log of ST is normally distributed with a mean of the expression here and a variance of the mean of the expression, first expression, and variance of the second expression. In other words, it is normally distributed with a mean of 3.687 and a variance of 0.247 squared, log of ST. Now, since log 40 is equal to 3.689, our required probability is 1 minus 3.689 minus 3.687 divided by 0.247, that is equal to 1 minus phi of 0.008, and which is equal to 0.4968. So, with this we come to the conclusion of this course. In this particular course, I have attempted to bring to you a package on path integrals. These path integrals constitute novel approach to contemporary problems in a variety of areas in multiple disciplines like statistics, quantum mechanics, quantum field theory, quantum gravity, and then they are also finding applications in economics, in finance, and condensed matter physics, and so many areas. The path integral is essentially a tool, a variation of traditional integration, where we try to integrate over all possible paths between 2 points in a particular underlying space. Please do connect with me on the discussion forum, and I'll also post supplementary notes covering each and every lesson. Thank you so much for being with me, and please be in touch on the discussion forum. Thank you.